You focus on structural behavior. Dynamics part is over because dynamics generally we feel it's a very boring or very complicated, right? Because throughout our undergraduate program we learn only the static method of analysis. We are not putting any focus on dynamic analysis, right? But here we want to study now structural behavior. So this type of irregularity we are observing in our structure. We find a stiffness irregularity, maybe a soft story structure, maybe a torsional irregularity. We talk about the asymmetric loading or mass irregularity. We talk about the liquefaction, ductile detailing. We talk about the short column effect. So this may be present in your structure. Ductile detailing, it may be good, it may be poor also. Right? What will happen? We'll see next. So first we take the soft story effect. If you look at this, now here generally the ground story is used for the parking, and so here only columns are provided, and when the columns are provided it will become soft because on the upper story column plus wall is present, so the upper part will become very stiff and the ground story will become soft. Whose stiffness is less than 70% of the upper story. This is going to happen in such cases, right? You can see this is the open ground story. Next, you can see this, for the parking we need space and we cannot provide walls at the ground story. Next, again this is open ground story. Next, open ground story, you can see this, yes. Next, so what is going to happen in open ground story? The stiffness of the ground story will become very less because you are not providing walls at the ground story. On upper story, you are providing the walls. So upper portion will behave as a rigid body, right? So the whole, there are 1, 2, 3 and 4 floors. These 4 floors will move as a single unit, right? And most of the deformations are concentrated at the ground story, right? Next. So what is going to happen? It will behave as an inverted pendulum, right? This total mass is concentrated at this level on these columns. That's all. So it behaves as an inverted pendulum. Next. So what is the effect? We can see. These are the damages observed in soft story buildings. Next. You can see this. The upper part remain intact. They are intact, right? But the ground story columns will collapse. This is a soft story failure. Next. You can see that again this 4 story is okay. Ground story columns will collapse. The people are saying that my whole building was sunk by 1 floor during the earthquake. They are saying, but then later on they come to know that the ground story columns were collapsed and the whole building came down by 1 floor. Next, you can see again here glass panels are provided and it is not going to provide any stiffness to your building. Upper portion is having the brick walls. It is stiff. Ground story become flexible. And you see, this is the power of nature. Within 2 minutes, it identifies what the soft story is. Right? Within 2 minutes. Next. You can see this height of both the buildings were same. Almost it came down on its knee. Right. Ground story columns were collapsed. Next. Again here this is a classical photograph from the Bhuj earthquake. The ground story columns were collapsed. And here also the way in which these buildings were collapsed, a torsion also taken place in this direction. Torsion. Right. Next. So what can we do? We can go for the masonry wall at the ground story, one option. But if you provide the masonry wall, then you are sacrificing your parking. Now where will you park your costly cars? It's the problem. So you cannot go for the masonry wall at the ground story. So what you need? You need a shear wall. So you provide a shear wall, and when you provide a shear wall, you have to be very cautious. You have to provide a space in which you can park the cars. Right. So shear wall will give you enough stiffness, and generally they are saying 20% stiff shear wall generally reduces the soft story effect. Right. But how to provide the shear wall? The shear wall must be provided symmetrically. They are saying symmetrically. Don't provide in an unsymmetrical way. Right. Again, the provision of shear wall in a symmetrical way is always a problem because we are working with the architects. So shear wall is again. Go ahead. So here, sometimes what we do, a concentration of the wall, shear wall is on one side, right? The shear wall is not allowed on the front side because we need a good architectural appearance. So therefore, you can place a shear wall on the rear side. In that case, you are making a structure unsymmetrical. Next, and for example, here the lift valve is put on the back side, and here there are columns. So this portion will become very stiff. This will become very flexible. In that case, what is going to happen? What is going to happen? Torsion is going to come. Right. Next. So center of mass and center of rigidity is not matching, and torsion is supposed to come. Go ahead. And this is what is going to happen. Your slab is going to rotate. Now column is attached to it. So column will observe the twisting. The slab will rotate and column will observe the twisting. So you have to design your column for the additional forces due to the twisting. Next. So these are the failures you can see. These are failures due to the torsion. Next. You can see these are the asymmetric shear wall which is provided, and we have seen the damages. Next. 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 So the model which is developed to show this behavior, right? So this is the moment resisting frame with shear wall model was developed. Go ahead. In which these are the dimensions which are given, which are used during the experiment. These are the floor plates, column dimension, shear wall. It is described. Next. And what we want to study? We want to study what is the behavior of a bare frame model. Right? Bare frame model means what? Without shear wall, only with the columns. Right? Model with the columns only. Then we put a shear wall. Right? Then we test a model with a shear wall. So shear wall is provided from the ground story to the top. And then to study the response of the soft story model, to study the response of the asymmetric model, to study the response of the mass irregularity. This is what we want to study. Next. So this is the frame without shear wall. This is the bare frame model. This is the bare frame model. Right? Only column, the slab is supported on the columns. Next. And this reading has been taken of acceleration versus time. Next. And these are the peak acceleration which is observed. Peak acceleration at the base 0.346 g, 0.44 g, 0.52 and 0.61 g. So up to 0.61 g, that is recorded by the sensors. And the displacement, you can see 16.3, 31.3, 52.2. Right. So what is the interstory drift here? Almost 20. What is the interstory drift here? Almost 16. And here 16. So the deformation is almost distributed along all the floors. Right. So interstory drift, you will not find irregularity. Next. Then we will test the model with the shear wall placed all along. Next. And then again we take the reading. Now shear wall is placed, so your structure will become stiff. Your structure will become stiff, so it is going to attract higher earthquake force. And you can see the acceleration is increased. Earlier it was 0.6 g, which was the maximum. Here you have 2.2 g, 2.2 g, which is very high. Right? So when you make a structure stiff, definitely your structure is going to attract higher earthquake force. Right? Higher earthquake force, because it is going to experience higher acceleration. What is the displacement? Advantage is displacement. When you make a structure stiff, you are definitely get the advantage. Displacement will reduce. What is the displacement? Earlier it was a 53 something. Now it will become only 20. So when you make your structure stiff, it is going to attract higher earthquake force, but at the same time deformation is reduced. That is the advantage. Right? Next. Then this is the third case. When the shear wall is not present in the ground story, shear wall is present on the upper story. Right? Now, what will be the behavior? So this will become very stiff. This will become flexible. So this is a soft story. Right? We'll see. What are the readings? Next. These are the readings we have taken. Next. And if you look at this, the acceleration was reduced because your structure became flexible. So the acceleration came down 2.23 with the shear wall, full shear wall, it came down to 1.056. And if you look at this, these are the displacements. The displacement is 40.7 at the third story, 35.6 and 29.8. So total deformation is 40 at the top story, and on the first story it is 30. Means what is the deformation at the how many percentage at the ground story? Almost 75% deformation is focused at the ground story level. 75% deformation at the ground story level, right? So which is very dangerous. Next. Then we put a unsymmetrical shear wall. We put a shear wall on one direction, and no shear wall on the other side. So this part will become very stiff. This part will become flexible. So in that case, what will happen? We will see that. Next. Next. And again, you can see what is going to happen. Torsion is going to come. When the torsion will come, your slab is going to rotate like this. So you get acceleration not in one direction now. You will get acceleration in two directions. This direction as well as this direction, because your slab is going to rotate. Now you can see this is the peak acceleration in x direction as well as you get the peak acceleration in another horizontal direction, z direction. Right? Earlier you receive acceleration in only one direction, but now slab is rotating, so you are going to get two accelerations in x and y direction, x and z direction. And these are the values of acceleration. Next, you will see some videos of the test. This is what we want. Just easy on that at top. Yeah. Look here. Great. This is known as formation of plastic hinges. This is the failure, and failure generally occurs at top and bottom of the column.
It's hot.
Just touch karo. And a tremendous energy release when the failure takes place. And I'm an inelastic stage में पहुंची हुई है. It is not an elastic stage.
Ultimate
Ductile material. Then it fails.
Linear stage की yield था बन जाओगे. Non-linear stage.
This is what we want. When the two structures are very close to each other, then what is going to happen? They will hit each other. They will collide with each other, right? So that is known as the pounding of structures. So when two structures are very close, what will happen? We'll see. So these are the two structures. Now these two structures having different frequencies, right? So the behavior of both the structures will be different. Now, suppose if I am saying the frequency is 5 Hertz, for the 5 Hertz frequency, both the buildings is going to respond in a different way, right? If both the buildings will have a proper understanding and they will vibrate like this, Right? Nothing is going to happen. No pounding is going to take place. But as the frequency is different, nature is different, so when the shaking is taken place, they will move towards each other. Right? So if the proper gap is not maintained, then they will hit each other. Right? And we'll see what will happen. Here you can see this is the slab which is hitting the column. Slab is hitting the column. Now we have designed this column for vertical load, means gravity loads. We have designed this column for the lateral load, even for the earthquake also, but we have not designed for this impact on the slab. And when the impact will come, we are knowing the value is almost double as compared to the static load. Right? So we have not designed this column for the impact, and this column may fail. We'll see this next. You can see due to the pounding, the damage has been observed. Next, you can see due to the pounding, this structure will fail. Now, who will sacrifice? The weaker will sacrifice all the time. Right? So here the weaker building will collapse. Next, the top story, again the pounding has been taken place and this portion was collapsed. Right? Next, here again the failure has been observed. Next, you can see this. Next, so when the two structures are close to each other, they will hit each other, they will collide with each other, and which is not a good condition for us. So only important thing is you have to provide a proper gap, and this gap is required. You have to design the gap. Right? You have to design this gap. And how to design the gap? Next, how to design the gap? You have to calculate the deformation of these two buildings, and you have to assume that these two buildings are deflecting towards each other, right? So you have to assume maximum deformation of one building in this direction, another building is deforming in this direction, and that deflection you have to calculate, and then you have to multiply. What is the drift allowed in the code? 0.4%, right? That is the allowed. Multiply by R factor. That is the value of the deformation you have to allow as a gap. Right? Next. So we talk about the model without pounding of slab with the column and pounding of slab with the slab. We'll see this, what will happen. Next. Next. So here the simple models where this slab is hitting the slab, and in this case this slab is hitting the column. Right? The slab is hitting the column. What will happen? We'll see. Next. Next. These are the readings which have been taken. Next, you can see when these are the pounding between the slab and the column. You can see the spikes. When the hitting is taken place, you will have a spike there. Alright. So you can see the spike here. You can see the spike here when the collision is taken place. Next. So here you can see the peak acceleration is 0.34 g. Now 0.34 g is not a small acceleration, right? What is the acceleration observed during the Bhuj earthquake at Ahmedabad? At Anjar, for example, what is the acceleration observed? The acceleration recorded at Anjar was 0.6 g. 0.6 g, that was the ground acceleration, right? This is a record. Now, if you use the spectra given in the code, what is the magnification you are going to get? 2.5. So 2.5 multiplied by 0.6 means it is 1.5 g. So the flow of your structure may have observed 1.5 g acceleration at Anjar. This is possible, right? Now you assume, you think that the load which is acting in the vertical direction is W. 1.5 times W is acting in horizontal direction. Now, is your building is comfortable? For vertical load, your building is comfortable, but your building is not comfortable for the horizontal force, right? You see, when we apply, when we want to lift a load on our head, we are comfortable, but if somebody will push you, you will lose your balance, right? The same thing is happening with the structure. Your structure is not comfortable with the horizontal loading. Reason is, the elements are vertical, they are transferring the load. You apply the horizontal loading. This horizontal load is supposed to transfer in the vertical direction. That is the problem, right? So here, this is the acceleration which is observed. This is maximum 0.75 G at the second story. And displacement, you can see these are the displacement. Next. And important thing is this, what is the force due to the pounding taken place? Now what is the additional force? Almost 34 Newton. That is the force applied at the column level. Now this is not a small force as far as this model is concerned, right? This is almost 26 Newton, right? So we have not designed our column for this impact force, right? Next. You can see these are the impacts. These are the pounding of slab to slab, slab to slab. Now the slab to slab pounding is taken place very fast. You can see these are the spikes where the collision is taken place. Next. And again, you can see the displacement and implicit in the force. Next. And again, this much force is applied, right? And we have not designed our column for this force, and that's why these columns are failing. Next. And we see the videos.
बंद कर दो रिकॉर्डिंग।
We talk about the buildings with the re-entrance corner. If we talk about the L-shaped buildings, C-shaped buildings, S-shaped buildings, we are saying these buildings are not good from earthquake point of view. Now, question is why they are not good for the earthquake point of view? Yeah. Because they are not coming from a different planet. It's from the same planet. But why they are not performing well? What is the reason? So you want to study that part. Good. So we can see such kind of structures, right? So here we are knowing that this is a E-type building, for example. Then the columns are placed somewhere here. So when the shaking starts in this direction, then 1, 2 and 3, they may be strong, but this portion is very flexible in this direction. So the deformation of this slab and deformation of this slab may be different, right? So in that case, these corners become very important for us. These corners are more vulnerable because they are subjected to different type of deformations. Alright, go ahead. This is a L-shaped structure. The L-shaped structure, this corner is vulnerable because when the shaking starts, this portion is very stiff, this portion is very flexible. In that case, right? Because shaking takes place in one direction. So this may be stiff, this may be flexible. This is possible. So in that case, the one portion will move more, another will move less, and in that case, the corner will observe different deformations. So that is known as a re-entrant corner, and this re-entrant corner is vulnerable to damage. Next, you can see these are the structures generally we are designing. Right. Next. This. Next. Next. Right. This is the seeker, which was collapsed in 2001. This is a ground plus 10-story building located in Ahmedabad. Only two buildings were collapsed. The ground plus 10 story. One is Mansi, another is Seeker. And Seeker is a C-shaped building. And here, one portion of this C building was collapsed. And one of the reason is it was a C-type building. I'm not saying that was the only reason in Seeker. There are many reasons we are knowing, but one of the reason is this. Next. So the model testing was taken up, right? So what we have done, we said that okay, we develop a model in which we can create such kind of effect. We'll see that. Next. So we create a model like this. It will be an L-shaped model. Next. So you can see this is an L-shaped model, right? Now, this is a particular segment in which only 4 columns are there. If you look at this portion, then how many columns you have? 1, 2, 3, 4, 5, 6. So this orange part is having 6 columns, while the white part is having only 4 columns. So this portion is having a less stiffness as compared to this. This is stiffer, right? So we'll see what will happen in this case if this building is subjected to the shaking, right? So what we do, we have connected these two portions by a link provided at this point and at this point. So we have connected by a link, right? And we'll see the behavior, and then we'll separate this link and we allow both the structure to move separately. Then what will happen? We'll see next. So again, same data has been taken. This is some dynamic acceleration time history that is to be analyzed. Means post analysis has to be carried out and to find out the maximum acceleration. Next, and you can see these are the accelerations and displacement value have been taken up by the two buildings. Next, same way without separation it has been taken up. Next, yeah. We focus on the behavior part and we see the.
इमरजेंसी प्रेस करो
એ કાંઠાના બધા આપણો બધોય વાળો થઈ જાય આપણો